In September 1859, telegraph wires across Europe and North America started throwing sparks. Operators jerked back, shocked through their own keys, and a few machines kept sending with their batteries disconnected. Running on electricity, the sky pushed through the lines. That was the strongest solar storm on record. So what happens if a superstorm that size hits Earth today? The storm carries the name of Richard Carrington, the British astronomer who watched a patch of the sun flash white on September 1st. That flash marked the launch of a coronal mass ejection, around 1 billion tons of magnetized plasma hurled off the sun toward us. A typical ejection needs 1 to 3 days to cross the 150 million kilometers to Earth. The Carrington cloud made the trip in about 17.5 hours, averaging more than 2,300 kilometers per second. It slammed into Earth's magnetic field and wrung it like a rag.
Here's why that reaches you. A shaken magnetic field generates electricity. When the field above a continent lurches, it drives current through any long conductor on the ground. Power lines, pipelines, rails. In 1859, the longest wires on Earth belonged to the telegraph, so the telegraph took the surge. Today, they belong to the power grid. A smaller storm already ran this experiment. On March 13, 1989, a geomagnetic storm hit Hydro-Quebec and the grid collapsed in about 90 seconds. 6 million people lost power for roughly 9 hours in a Canadian winter. The same storm wrecked a transformer at a New Jersey nuclear plant. Scale that up to Carrington size, and transformers become the story. Storm currents drive a high-voltage transformer outside its design range and cook its core. Each one weighs up to 400 tons, costs millions of dollars, and takes a year or more to replace. A 2008 U.S. National Academies report put the worst case at continent-scale blackouts, $1 to $2 trillion in first-year damage and recovery measured in years. Other engineers expect protections to trip first, giving days of blackout, not years. Satellites face it with no atmosphere to hide behind. Charged particles scramble their electronics, and the heated upper atmosphere swells outward and drags on everything in low orbit. In February 2022, a minor storm, nowhere near Carrington-class, pulled 38 freshly launched Starlink satellites out of the sky. The storm churns the ionosphere too. The charged layered GPS signals cross to reach your phone. Position errors grow from meters to tens of meters. The worst moments break the signal outright. Long-range radio blacks out for hours, so airlines pull flights off the polar routes. They did in October 2003, the same week a Swedish city lost power. Here's the twist. The full test nearly ran. On July 23, 2012, the sun fired a Carrington-class ejection straight across Earth's orbit, and it hit nothing. Our planet had passed that point about a week earlier. Estimates of the odds of a direct hit run from under 2 to about 12% per decade. One number shouldn't scare you: your own radiation dose. The atmosphere and magnetic field absorb the incoming particles. The storm can't hurt anyone standing on the ground. The real risk rides above that shielding with the astronauts, who'd wait it out in the best protected corner of their spacecraft. For everyone else, the danger arrives through the wall socket, not the sky. And while the grid fights for its life, the sky stages its biggest light show since Carrington's storm. In 1859, auroras burned over Cuba, Hawaii, and Colombia. Miners in the Rockies woke near 1 a.m. and cooked breakfast, and people read newspapers by the glow. A repeat would hang curtains of red and green over cities that have never seen them. So here's the question for the comments. Hardening the grid would cost billions, and the storm keeps no schedule. It might come next spring or wait a century. How much should we spend on a disaster with no arrival date? And the sun isn't the only threat holding our address. What a single falling rock does to the Pacific Ocean is on your screen right now.